In section 7.1, we look at arithmetic and geometric sequences. Let's start with the definition of a sequence. A sequence is a function f of n, whose domain is the set of all non-negative integers. In other words, n can be numbers like 0, 1, 2, 3, 4, etc. N cannot be a fraction, a negative number, or an irrational number. And the range of the sequence is a subset of all the real numbers. The numbers f of 0, f of 1, f of 2, etc. are called the terms of the sequence. For a non-negative number n, it is conventional to denote the term that corresponds to n by a sub n rather than writing f of n. And we will use both notations. So let's start with a very simple example. Suppose I gave you f of n is equal to n squared. This function can represent a sequence, and n is going to be the numbers 0, 1, 2, 3, 4, etc. Let's write down the first several numbers in this sequence. So the first number would be f of 0. The second number will be f of 1. The third number will be f of 2, and we can keep doing this as long as we wish. And now what is f of 0? Well, f of 0 means you plug 0 into n squared. So the first term of our sequence would be 0 squared. The second term would be f of 1, which is 1 squared, and then 2 squared, 3 squared, 4 squared, etc. And so these numbers turn out to be 0, 1, 4, 9, 16, and onward. And basically what we're saying is we would call this number, instead of calling it f of 0, we could call it a sub 0. The first number, instead of calling it f of 1, we can call it a sub 1. Actually, it's the second number, sorry. The next one we can call a sub 2, right, and onward. So this is just a more convenient notation. So in the beginning, when we defined the sequence, we could have said a sub n is equal to n squared. Now let's take a look at special types of sequences. The first special sequence is the arithmetic sequence. The definition of an arithmetic sequence says that each term of an arithmetic sequence is given by the rule a sub n equals a sub 0 plus n times d, where n equals 0, 1, 2, 3, etc. So a sub 0 is what we would call the starting value, and d is the common difference between the successive terms. So you can calculate d by subtracting any two successive terms. But rather than dwell on this definition, let me just give you a quick example of an arithmetic sequence. Suppose I give you the numbers 3, 6, 9, 12, 15, and so on. These are the terms of an arithmetic sequence. The common difference from one term to the next is how much you have to add to get to the next term. So to get from 3 to 6, we have to add 3. To get from 6 to 9, we also have to add 3. From 9 to 12, again, adding 3. And every successive term after that comes from adding 3. So we would say that the common difference is 3. Now, another way to calculate that common difference would be to subtract any two successive terms. So notice that if we subtract 6 minus 3, 9 minus 6, 12 minus 9, 15 minus 12, and so on, these are all equal to 3 as well. So in this arithmetic sequence, the first term, which we call a sub 0, or we also call that a naught, okay, that's another way of saying a sub 0, that first term, a naught, is 3, and the common difference is also 3. Let's take a look at a second example. Suppose I give you the terms 4, -2, -8, -14, and so on. This is also an arithmetic sequence. You can see the first term of the sequence, A0, is 4. And what is the common difference? Well, to get the common difference, you can think of that two different ways. One way to think of it is, what do I have to add to get from 4 to -2? Well, you have to add -6. And to get from -2 to -8, you would also have to add -6. And from -8 to -14, we would also add -6. So it appears the common difference here is -6. And of course, another way to get that common difference is I could just subtract the second term minus the first term, so -2 minus 4. Or I could have subtracted the third term minus the second term, so -8 minus -2, and so on, right? I could take -14 minus -8. And if you do the math on each one of these subtractions, you will notice that you get -6. And so that would be our common difference. So an arithmetic sequence is a sequence where each time you move from one term to the next, it just increases or decreases by the same amount. Now, when you're trying to find the formula for an arithmetic sequence, it's going to be very useful to keep this formula here in mind. Let's take a look at an example. So here we have table 1 gives the first 4 terms of an arithmetic sequence. So here are the n values, and here are the actual terms of the sequence. What we want to do is find the rule corresponding to the given sequence. So from the previous page, we know that an, which is our rule, is going to be a0 plus n times d. So to get this, we need to know what is a0 and what is d. Well, clearly a0 is the term of the sequence corresponding to when n equals 0, and that term is -1. And the common difference we can get by thinking about what number do we have to add to move from one term to the next. So when I go from -1 to -3, I'm adding -2. When I go from -3 to -5, I'm adding -2. And every time I'm adding -2. That's one way to calculate that. Or we could subtract successive terms. So again, I could take -3 minus -1. That would be -2. I could also do -5 minus -3. That would be -2, right? So D is -2. So once I have that information, the rule corresponding to the given sequence is AN is equal to the first term, right? A0 is the first term, which is -1, plus n times D, and we know that D is -2. So this is equal to -1 plus n times -2, that's going to be minus 2n. So the rule is an equals -1 minus 2n. And for the second part of this problem, they say, use your rule to find a sub 10. So this is a much easier problem. To find a10, all we have to do is take our rule here, and we're going to let n equal 10. So a10 would be -1 minus 2 times 10. This is -1 minus 20, which is -21. And one thing you have to be a little bit careful of is when you say a10, you want to think of this as being the 10th term of the sequence, but actually it's the 11th term, right? And it's the 11th term because we're not starting at n equals 1, we're starting at n equals 0. So you have to be kind of careful with that because intuition would tell you that a10 is the 10th term. But again, because in this book they like to start at 0, a10 is actually the 11th term. So in the next example, it says, suppose two terms of an arithmetic sequence are A8 equals 10 and A12 equals 26. What is the rule for this sequence? Okay, so again, we know the rule is AN equals A naught plus N times D. And what we need to know the rule for the sequence is we need to know A naught and we need to know D. And we don't know either of those because they did not give us the first term of the sequence, right? And they also did not tell us the value for D. And these are not successive terms, right? A8 and A12 are not successive terms, so we cannot easily calculate D because of that. So there's a couple of different ways to do this. Let me go ahead and show you one method. So one way to do it is to let n equal 8. If n equals 8, we have A8 equals A naught plus 8 times D. And if we let n equal 12, we know that A12 is equal to A naught plus 12 times D. So again, I'm just plugging the value of either n equals 8 or n equals 12 into this equation. Now, we know what A8 is, so we can actually write this equation as 10 equals A naught plus 8D. And this other equation, we know A12 is 26, so that would be 26 equals A naught plus 12D. And now all I have to do is subtract these two equations. So let me write them down below here. And if I subtract these two equations, I'm taking the second equation here, and I'm going to subtract the first equation. When I subtract that, I have to subtract the whole thing. So what happens here is I get A naught minus A naught, that cancels. We get 12D, take away 8D, that's 4D. And on the other side, 26 minus 10 is 16. And from here, we know that D is 4. Now, once we know D is 4, we can plug that into either one of these equations up above. So if I plug it into the first one there, I get 10 equals A naught plus 8 times 4. And this is 10 equals A naught plus 32. And if I subtract 32 from both sides, we get A naught is equal to negative 22. So now we have the value of A naught and we have the value of D. And we know that AN is equal to A naught, which is negative 22, plus N times D. D is 4, so it will be 4N. So this should be the rule, and of course you can check your answer. When you let n equal 8, you get negative 22 plus 4 times 8 is 32, and that's 10. And when you let n equal 12, you get A12 is negative 22 plus 4 times 12. 4 times 12 is 48, plus negative 22 is 26. So now we have the formula for any term of this sequence. The next type of sequence I want to talk about is the geometric sequence. And the geometric sequence is defined by the rule that you see here. AN equals A naught times R to the N. Once again, N equals the values 0, 1, 2, etc. A naught is again the starting value of the sequence, and R is the fixed number by which any term of the sequence is multiplied to obtain the next term. So the way a geometric sequence works is you're not adding or subtracting the same number to get the next term. You're multiplying by the same number. So an example of a geometric sequence, let's just take a simple example. Say the first term is 5, and let's say I'm going to multiply by 2 every time. So the next term would be 5 times 2, which is 10. The next one would be 10 times 2, which is 20. 20 times 2 is 40. 40 times 2 is 80. 80 times 2 is 160, right? And we could keep doing this. You can keep multiplying by 2 every time. So the way a geometric sequence works is you are multiplying by the same number every time. And that number does not have to be a positive number. It does not have to be a whole number. You could be multiplying by a fraction or a negative number, but that's the basic principle. We multiply by same number each time. So if you have the terms of a geometric sequence, one way to get that common ratio that we call that R, it's the common ratio, is to just ask yourself, what would I have to multiply 5 by to get 10? That's relatively simple. But the other way to do it, if you look at the formula up here, is you could just take any term divided by the term before it. So if I pick any two successive terms and I just divide them, that will give me the common ratio as well. So I could take 40 divided by 20, for example, right? That would be 2. Or I could take 320 divided by 160. That would also be 2. So in a geometric sequence, we are just multiplying by the same number every time. So in our first example for geometric sequences, it says find the rule for the geometric sequence with A2 equals 12 and A3 equals 24. So let's remember that AN is equal to A naught times R to the N. That's the rule for the formula, where N is equal to 0, 1, 2, 3, etc. So one thing I can do here is I can find R very easily in this problem because they gave us A2 and A3. So if I just take A3 and divide it by A2, that will give us R. So that would be 24 divided by 12, which is 2. So we know that R equals 2. Now once we have R equals 2, our formula now can be rewritten as AN is equal to A naught times 2 to the N. So the only other thing we need to know the formula for the nth term is we need to know what is the first term. So I can use either one of these to figure out the first term. So I'll just use the fact that A2 is 12. So since A2 is 12, we know that if n equals 2 in this formula, we would have A2 is equal to A naught times 2 to the 2. So again, I'm just plugging in n equals 2 in both of these spots. And we know that A2 is 12, and that's going to be A naught times 2 squared is 4. And so we know that A naught must be 3, right? Because we know that 3 times 4 is 12. Okay? So we now have A naught and we have R. And so the formula for the nth term we can say is AN equals A naught, which is 3, multiplied by R, which is 2, to the n power. And you can write it like this, but you can also write this as 3 with a dot times 2 to the nth power. Now, either one of these is okay, but I think the parentheses is probably a little bit safer. So I tend to use parentheses around my R instead of just a dot. And this is especially true if R turns out to be negative. You definitely do not want to use the dot. So probably it's best to use this notation. In our next example, it says find the rule for the geometric sequence with terms A2 equals 32 and A5 equals 4. All right, so once again, we know that AN is equal to A naught times R to the N. So we need to know what is A naught and what is R. Well, again, if we know n equals 2, right? Well, we know A2, so if n equals 2, if I plug 2 into this formula, I'm going to get A2 equals A naught times R squared. And if n equals 5, we know that A5 is 4. So if I plug n equals 5 in here, we get A5 equals A naught times R to the 5th. And then again, we know what A2 is and what A5 is. So I'll take A2 is 32, plug that in. That gives us 32 equals A naught times R squared. And in this one, A5 is 4, So we get 4 equals a naught times r to the 5th power. And what you can do here, a couple of different ways to solve this, but the easiest way to do it, in my opinion, is to just solve for a naught in each one of these. So in this first equation, a naught is going to be 32 divided by r squared, right? If I'm solving for this, I need to divide both sides by r squared. And in the second formula here, a naught will be 4 divided by r to the 5th. And we know that those are the same a naught, so they have to be equal to each other. So this has to be equal to this. So 32 over r squared must be equal to 4 over r to the 5th. If I cross multiply, we get 32 times r to the 5th must be equal to 4 times r squared. And then the easiest way to solve for r is to just go ahead and divide both sides by 4r squared. This is going to give us 8r cubed is equal to 1. And then we can solve for r by simply dividing both sides by 8. And then finally just taking the cube root of both sides. And that is going to give us r is equal to the cube root of 1/8 is 1/2. Now, as soon as I know r equals 1/2, I can take that value, come up here and plug it in. And I can plug it into either one of these equations. I'll just plug it into the first one. That's going to give us 32 equals a naught times 1/2 squared. That is 32 equals a naught times 1/4. And then multiplying both sides by 4. 4 times 32 is 128 is equal to a naught. So now we have the first term, a naught, and we have the common ratio, and now we can say the nth term, or the an, I should say, is 128 multiplied by 1/2 to the n. And that is the formula for any term of this particular geometric sequence. Now, before we move on, I actually wanted to come back to this problem and just kind of show you a slightly more intuitive way that you could solve for r. So we have this geometric sequence here. We don't know what a naught is. We don't know what a1 is. We do know that a2 is 32. We don't know a3. We don't know a4. But then we know a5 is 4. Okay? So what we're going to do here is we're going to say, well, the way you move from term to term in a geometric sequence is you're going to multiply by r. You're going to multiply by r again. And you're going to multiply by r again. So to get from 32 to the number 4, we take 32 and we multiply by r 3 times. So we take that number 32, multiply by r, multiply by r, multiply by r. That gives us 4. And notice that this is 32 r cubed is equal to 4. And then if we divide by 32, we get r cubed is equal to 1/8. And from there, we can get r is equal to the cube root of 1/8, which is 1/2. So this is a little bit more of an intuitive method for solving for r. And then, of course, once you get r, you would have to come back to your formula here, plug in the value of r equals 1/2, and then you can use the fact that a2 is 32 or a5 is 4 to figure out what a naught is. But to figure out that first part, solving for r, you can do it the way I did it a couple of minutes ago, or you could also do it this slightly more intuitive way. Either way works.